A strange pattern is emerging in AI. The biggest gains are no longer just about scaling models bigger, but about separating roles, compiling intent, and making systems cheap enough to run in the real world. One line of work shows a small Qwen-based system beating a much larger model by turning fuzzy instructions into executable adapters. Another shows ByteDance's Seed 2, zero pushing toward production-grade agentic intelligence across math, vision, code, and search. And a third suggests transformers improve when prediction and memory stop fighting each other. The common thread is efficiency with structure, and it's a lot more important than it sounds. Let's explore the first paper, Program as Weights, a programming paradigm for fuzzy functions. Program as Weights, PAW, from researchers at the University of Waterloo, Cornell University, and Harvard University, reframes fuzzy software tasks as compile once, run locally neural programs. A natural language specification is first converted into a discrete pseudoprogram by an off-the-shelf Qwen-34B instruct 2507 compiler, then into a per-function PEFT artifact by a trained 4B Qwen3 LoRa compiler. The resulting program is executed by a frozen Qwen306B interpreter. Trained on FuzzyBench, a 10M example dataset spanning 29 thematic versions and 800 plus task categories, PAW's default LoRa instantiation reaches 65.7% exact match with rank 64, versus 50.4% for prefix tuning and 9.8% for direct prompting. On the verified FuzzyBench test set, the Qwen306B PAW system achieves 73.78% exact match, surpassing direct prompting of Qwen332B at 68.7%, while using about 50 times less inference memory, and it runs at 30 tokens S on a MacBook M3 with a 430 megabytes shared base plus a 23 megabytes per program adapter. The paper also shows a multimodal extension using Qwen3 VL4B as compiler, where PAW LoRa reaches 0.274, 0.414, and 0.552 on circuit, chemical, and music diagram tasks respectively, and reports only minor degradation under heavy, noisy specification perturbations because the pseudo-program denoises the input before execution. Let's explore the second paper, Seed 2, Zero Model Card Towards Intelligence Frontier for Real-World Complexity. Seed 2, Zero Model Card, released by ByteDance Seed, presents a production-oriented model family that spans Pro, Light, and mini variants and is explicitly optimized for real-world complexity rather than isolated benchmark wins. The paper argues that the key bottlenecks in deployed AI are multimodal understanding, low latency inference, reliable complex instruction following, and long horizon agentic execution, then evaluates Seed 2. Zero across frontier math, coding, vision, video, search, and workflow benchmarks against GPT-5. 2, Claude, Opus, 4, 5, Claude, Sonnet, 4, 5, and Gemini 3 Pro, Flash. Seed 2, 0 Pro reaches 98.3 on AIM 2025, 3020. Codeforce's ELO, 35.5 on Putnam, 200 pass at 8, and 73.02% pass at 8 on 5 ICPC contests, while also posting 75.26 on a 912 case Chinese complex instruction benchmark, improving over Seed 1, 8 by 2.37 points. In multimodal evaluation, it sets state-of-the-art scores, such as 88.8 on Math Vision, 90.5 on Math Kangaroo, 92.3 on DA2K, 72.4 on DUDE, and Autoneo, Fem on Video MME. And it strengthens agentic search and research performance with 77.4 on Deep Search QA and 50.8 on research rubrics. The model card also emphasizes cost efficiency. Seed 2, 0 Pro, Lite, and Mini are priced at $0.47, $0.09, and $0.03 per 1M input tokens, with output pricing as low as $0.31 per 1M tokens for Mini, positioning the series as a lower-cost alternative for large-scale enterprise deployment. Case studies show Seed 2, zero-solvent cryptanalysis, repository construction, GUI automation, and scientific reasoning tasks, including 231,061.93 cubic millimeters volume and 23,306.19 square millimeters surface area verification in FreeCAD, underscoring the paper's central claim that the model family is moving toward agentic, tool-using intelligence for production environments. Let's explore the third paper, the state prediction separation hypothesis. The state prediction separation hypothesis argues that a transformer's hidden state is overloaded. It must both predict the next token and store reusable state for later tokens. To test this, the authors at Cornell and Harvard introduced the state prediction separation transformer, which interleaves each input token with a dedicated is less than and predict is greater than slot. So prediction gradients and state preparation gradients flow through different streams. Across 5 model scales from 53M to 1/678B parameters, trained on FineWeb Edu, SPS consistently beats a standard transformer and 2 controls, 2x, memory, and delayed state. On FineWeb Edu validation NLL, SPS improves from 3.107 to 3.065 at XS, from 2.858 to 2.81 at S, and from 2.458 to 2.39 at XL, while generalization also improves. Corpus NLL drops by 0.090.15, and average zero-shot accuracy rises by 3.1 percentage points over ArcEasy, HelloSwag, PIQA, SciQ, and Lambda. The key result is efficiency. SPS reaches standard quality with roughly half the training data, matching standard's persistent KV cache footprint and staying within about 6 to 10% of its throughput, with peak memory held at 1.01 times standard. The analysis shows the gain is structural, not just extra compute or memory, because SPS routes more future loss gradient to the input stream and makes the persistent state 1.42.2 times more important at inference than delayed state. That's a wrap on today's AI paper highlights. Thanks for watching.